Hello everybody, my name is Tyler Lay and welcome back to my YouTube channel. This is the hydration episode. Hydration is one of the most mystical, misunderstood, but important times in the life of concrete. It is the birth of concrete. It's so crazy, exciting, and scary at the same time. It's pretty amazing stuff. I'm going to tell you kind of a conglomerate of a lot of the different experts' opinions. And I'm going to try to give you some data to see what people have shown and try to also show you some brand new, hot off the presses data that our research group has been collecting. And I hope together it helps provide a better story or insight into hydration. We're going to spend a lot of time on this sheet. Let's zoom in and explain the different parts. Start in the upper left-hand corner. This graph shows the concentration of different ions in solution. This is what's swimming around. This is moles per liter, like a concentration of chemical species. And here's calcium. Here's silicon, and the x-axis is time. And we have these different stages. Stage 0, 1, 2, 3, 4, and 5. We'll talk about each one of those stages. This line right here, here's the saturation level. We're going to be above saturation in certain time periods for calcium. The next plot. This is the rate of heat release versus time. If you've done an isothermal calorimetry experiment, then that's exactly what this curve is showing. And again, the different time periods, here we go, 0, 1, 2, 3, 4, and 5, have lines that go down. And we can see what the heat does these different time periods. Down here at the bottom, these are some engineering properties, things we're used to measuring. And this is showing relative values. This would be high, this would be low. And again, we have our different periods down here. And we can show our slump is decreasing during this time period. And this is called the induction period, or time 2, okay, or stage 2. And this is when we transport and place the concrete from stage 2 in the early parts of stage 3. Now, setting. Talked about that in a previous video with a Vicat needle test. Here's setting going up, 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 up. Happening again in stage 3. Here's strength growth. This might be compressive strength, tensile strength, flexural strength growth. Goes up and up and up and up and up and up. So these are the engineering properties. This is when we transport and place our concrete. This is when we mix our concrete. This is when we cure our concrete. Now I've got some pictures up here. Now, these are pictures based on some old conceptual models. Not everything's wrong about them, but not everything is right about these pictures as well. But we're going to use them as a starting point, and this is still the way some people teach hydration and talk hydration. So you should know kind of the different versions of the story, even if they don't all agree with one another. They're all hoping to get to a good place. So let's talk about stage 0. Stage 0, that's when the cement and water first meet. Ha! What an amazing, amazing time. This is when hydrolysis takes over. This is when those ions get in there, water molecules get in there and just rip apart everything they can get their hands on. They just tear, 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 tear. Right? And they tear apart the C3S, and they tear apart the C3A, okay? And they start out some of the early reactions. They start forming some early age hydration products. Early age calcium silicate hydrate, and some early age etronite. Now this etronite is a little bit of a mislabeled. A lot of people don't really know what happens. There's probably some kind of precursor material that forms that is still being studied. Okay? In the meantime, what you need to know is that at stage 0, there's a lot of tearing going on, a lot of ripping apart. And that's why, if you look at this heat release, look at it. It goes way up, 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 up. And look at the moles per liter. They go up, 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 of silicon and calcium. And then they start to go down. What does the heat do? It goes down as well. Let's go read what happens. Stage 1, the surface of the cement particle changes. This is the part that no one really understands what happens or what goes on. Why does it go down? Why do things stop going into solution? Why does the silicon go down? Well, probably because it's forming some kind of calcium silicate hydrate. But why does the calcium keep going up? Why does the heat go down? Probably because there's not as much dissolution going on, but we don't really know why. Some people say the surface chemistry or the charge may change. Something changes on the surface. The cement grains may be covered in an early age CSH or gel-like material. That's not totally right. I'll show you that coming up. We know that's not true. But we know that it becomes difficult for at least things to dissolve. Now this picture up here shows some kind of early age product forming on the surface, and some kind of eternite needles floating in space. Now, first of all, no one knows. No one knows for sure. But we do know that there's not a constant layer on the outside of the material, at least not that we can observe. But this idea that the surface changes, the charge or something else changes, I think that's possible. I think that's possible. Let's show you what I mean. My research group has been extremely fortunate to be able to make very important measurements at Argonne National Labs, at the Center for Nanomaterials, at the X-ray Nanoprobe. What a name. At Beamline 26. This is a synchrotron facilities where an electron beam goes around and around and around the ring, and we actually capture X-rays that come off different layers. And this is the Beamline where we can actually do experiments with these X-rays. Here's me inside the Beamline. The X-rays come down this tube. They're not coming down the tube when the picture's being taken. Okay? We have to leave the room. The X-rays come down and they interrogate our sample over here. Now the cool thing about this is we can use a technique called X-ray nano-computed tomography. It's like a CAT scan for materials. We can also use another technique called X-ray nano-X-ray fluorescence. Okay? Nano-X-ray fluorescence. So we can measure chemistry at this level as well. It's pretty awesome. Here's what one of the particle looks like. Very early age reaction. This is a C3s particle on the left. This is a 3D. This is not a model. This is a real measurement of the particle. We can take a slice out of it and look inside of it, okay? And it looks pretty homogeneous. It looks homogeneous. But if we look after, this is after it's been placed in solution, where some of the reaction has happened. We placed it in the solution and then stopped the reaction and took it out and imaged it again. After a short time period, we can see that certain boundaries or layers aren't reacted, and other regions are reacted a lot. This gray value means it's modified or it's changed. This gray value is actually calcium silicate hydrate type stuff. Yeah, and we can look inside of it, and we can see these pits being digged, these holes being dug inside. This is an example of a non-uniform reaction that's happening inside these cement grains. These big pits are an example of hydrolysis of the water molecules digging, but they're only digging in certain regions and not in others. And those pits are filling with hydration products. What? I know, let's see. Here's our 2D slices, 2D cuts from different regions from that 3D particle. And this is the top. This is what it looked like before, and then after, look at this big gash. And here is another layer. Here's before, and you can see this cut is in here, and then there's another crack that's happened inside the particle. And then here This is what the particle used to look like. And again, we can see this cut. And this region right here is being eaten off. What's going on? The water molecules are preferentially eating away certain parts of the particle, but not others. And those parts are backfilling. They're filling in with stuff. What does that mean? Here's a cartoon to show you what I'm talking about. There seems to be certain regions that have defects or damaged. They're not quite right. They're different. We get a non-uniform reaction. This etch pit, this big pit gets dug out, and there's lots of ions swimming around, tons and tons of ions. And that pit, that region in the pit, seems to get super saturated. How do we know? Because we've measured it. We've measured it, and we see material forming back in the pit. And that material has a chemistry that's pretty similar to calcium silicate hydrate. But over time, those materials will keep reacting, keep dissolving within the pit. Some of the ions will escape. That's why we see the calcium concentration continue to go up. But some of the ions get stuck in the maze of the hydration product. And what do they form? They form these crystals that actually, and we see them. We can see these crystals growing in the hydrated CSH. And these crystals may shut off this outside access of water. I know. Crazy, right? This is why I was telling you, these images at the top may not be exactly right, but no worries. These are really recent observations that our group's made. And there's other people making observations all around the world right now. But that pretty much takes us to the end of stage 1 and the beginning of stage 2, a very important period, the induction period. This is when concrete is transported from one place to another. This is when it's dumped out of the truck. This is when it's vibrated, consolidated, put in whatever shape that you want it to be. Okay? In this period, there's very little heat given off. The calcium concentration continues to increase, but it still seems to be difficult. It says over here for water to reach the cement grain. That's probably not quite right, but there's not a lot of dissolution occurring. There's not a lot of material dissolving and leaving away. Let me show you these pictures. There's stage 2. You can see the calcium go. Look at that. Super saturated levels, and the silicon gets lower and lower and lower. And here's this heat given off, and it's pretty flat. Now, this image at the top here suggests that the outside layer is totally covered. I'll show you a picture. That's not quite right. Here's a picture of a C3S particle before, 3D image before, and a 3D image after, a tomograph after. It's been reacted for 2 hours in this solution that's rich in calcium and gypsum, calcium and sulfate. And we can see that this is about the time period when it's in the induction period. And look, this gray area is the hydration product. There's certain regions that aren't covered at all. And there's other regions that are almost totally covered. It's nuts, right? Let's look at these 3 different slices, 1, 2, and 3. These 3 different locations. Here's the raw measurement before, and here's the raw measurement after. And here's where we've segmented them. We've separated them into different materials by using gray values. And we can see these different regions, like, for example, 3 here. There's certain regions that are not reacted at all, have almost nothing going on, no reaction, they look great. And then down here at the bottom, look, there's hydration product forming. What's going on down there? There's other regions over here where there's lots and lots of hydration product forming on these certain surfaces, but not on these others. What's going on? This is this non-uniform reaction I told you about before. It really has to do with this localized structure of the material. It's pretty nuts. So this induction period, this picture isn't quite right, but they did the best they could for for the knowledge they had at the time. But there's definitely regions that are totally bare here. right? But we've still got calcium hydroxide, we've got CSH, okay? And then we get to stage 3. Stage 3 is known as the acceleration period. The calcium concentration reaches this super saturated level. And we know that calcium hydroxide starts to form. It starts to form in solution, not within the CSH, out into the solution, okay? And we know the surface of the cement grain changes. This calcium concentration buildup may change the surface chemistry. We don't know for sure. This calcium hydroxide nucleation may break down some of the surface. I think there's some real potential to that. Something called osmotic pressure may break down the initial CSH. We know that CSH starts rapidly forming in this time period, and etranite needles start to nucleate on the surface, start to extend, and as they start to interaction with one another, you start to get initial set. So let's look at the graphs. Again, we're in stage 3. Calcium level starts to drop. Silicon level in solution never gets high, but we start to see this rate of heat given off. Tons and tons of heat given off. That means things are dissolving. This setting goes up. That means things start to interacting with one another. There starts to be impingement on these different hydration products. Okay, these hydration products are nucleating on the surface, right? They're nucleating and forming on the surface because it's reached a super saturated level. Let's look at the pictures up here. So this concept are these things start to grow on the outside, and these etranite needles, you can see them there. Now they're real etranite. They've hit the surface and they start extending, they absorb water, and that interaction is what causes this initial set to start to happen inside of our concrete. So then we reach stage 4. It's known as the deceleration period. Hydration starts to slow as CSH forms on the surface of the cement grain, and water can't easily access the cement grain. I think this is true now. And the reaction becomes diffusion controlled. What's that mean? It means it can only go as fast as water can get in to the reacting surface. Let's look at that, what it looks like here. So in this case, our calcium stays still around saturated. Silicon stays at a low level. And look at this, the heat goes down during this period, the deceleration period. But what happens to our strength? It goes up. Why does it go up? Because there starts to be interaction between the particles. These particles start to be able to transfer load between one another, and that's exciting. And one of the other great things about it is we've got some images of this time period. What we see in our experiments is we see hydration products starting to form in the solution, and they start to grow. And once they start to grow, they seem to cause these crystals that formed early on to shrink. And once they shrink and go away, reaction starts to happen again. The thing we don't understand yet, though, is reaction seems to happen in these pits, but it also starts to happen on these surfaces. These surfaces that didn't react before now for some reason become reactive, and we're not really sure why. And then hydration product starts to form everywhere. Here's an image. Here's a particle before on the left, and here's a tomograph after 10 hours. Look at all the hydration product all the way around it, forming it. And a lot of people think that it forms uniformly, but not necessarily. Let me show you what I mean. Again, see these 3 dotted lines? We're going to show 3 different cross sections inside the particle. Here's the particle before, and here it is after. And we've segmented. We've shown you this region. This white is the part that's not reacted, and this gray is the part that has reacted some. Again, look at it. It's changing. It's reacting. Certain layers, though, certain regions, it's not reacting in a very thick layer, a very thin layer. And in other regions, it's pretty thick. Okay? Look at this. This is what it looked like here originally. This part has like totally reacted. And this part down here, it's not reacted almost at all. Almost none. But just a little bit. This is kind of complicated. This is a lot of stuff we don't totally understand. And now we're finally in stage 5. This is when hydration continues at a slow rate as long as water is available. As long as you provide water, hydration will continue to happening. But if you remove the water, it stops. It stops. And it's almost impossible to get it going again. It's almost impossible to get water down there into those pores and keep it going again. And that is why curing, keeping the concrete moist, right? And not too cold, not too hot, is really important. Thanks. Take care.